Hey everybody. The point of today's exercise is to kind of get the basics and principles of fiber testing, and in particular OTDR testing. OTDR testing stands for optical time domain reflectometer, which is why nobody says it, OTDR. So with OTDR testing, it's used for finding where an issue is. So we've got a network owner here, and they've got their cable that comes from their patch panel, goes into a handhole, goes down the road, and maybe there's a bend in it, and eventually it comes to this customer's house. So an OTDR is a testing tool that is going to be used here at the CO, and depending on what type of network architecture, if somebody is using splitters or PON, they are going to be testing from the house side of this. But once we take this magical box and plug into this network, it's going to identify where issues are and what type of issues it is finding. And I think there's some basic principles that we can cover here today that will help you understand and advise to your clients on testing with a little bit more comfort and confidence in what you're talking about. So first off, an OTDR, it's basically an expensive stopwatch. You tell the machine go, and it starts shooting a spitball of light down the fiber cable. And it knows what the speed of light is. So it's timing. How long does it take for this spitball to get back to me? Okay, when I shot that spitball out of our laser, if you are wondering what's going on with lasers and spitballs, there's another video that kind of will introduce you to the principles behind wavelengths and light. So the OTDR shoots a spitball, and it knows how fast this spitball is going to travel down this network. And it's timing it. With that, it knows how far light has traveled. The second part that this fancy stopwatch does is it measures how light is coming back to it. So I said OTDR stands for optical time. So we just talked about the time. Domain, I don't really know why domain. Somebody can comment or help me understand that. But reflectometer. So it's looking at reflections of light. So as this spitball travels down this fiber cable, there is always a steady stream of light. So as this travels down our fiber cable, a steady stream of light is always coming back to our OTDR. And that amount is always slowly decreasing. So in that previous video, we talked about our power source being a laser with a fiber optic network. When we're testing, the power source is now becoming our OTDR. That's shooting the spitball. So let's say our OTDR has a power of 40. It's shooting that spitball at 40. When it travels down a fiber cable, if there's absolutely nothing wrong with that fiber cable, it's not spliced, there's no connectors on it, nothing. It's just going to be this straight line. That is called attenuation. It's inherent loss to a fiber cable. When you look at specs, somebody might say like, hey, I want Corning glass, SMF 28, whatever spec. When you go look at what the attenuation rate is, that's the inherent loss involved with it. But it'll say 1310, 1550, and the loss, it might be 0.2/0.25 dBs per kilometer. So basically, it's giving us a rate at how much light or power it's going to lose as we travel. So in this scenario, this axis right here, we're at 0 miles. This is where our CO is at and where our patch panel is at. We're injecting 40 decibels of power with our OTDR, and it's traveling 5 miles to this customer's house. And in this scenario, we don't have any issues or problems. Now, when our spitball of light travels from the CO over to the customer's house, inside their house, we've got that box called a NID, or customers might call it an ONT. There's different names for it. But inside of that box is a little magical device, the ONT, and that accepts a range of light. So inside of this box, there's a little electronic thing. It's about the size of a hockey puck. Sometimes they're bigger, and they accept a range of light. So that device, your ONT, is going to say, hey, I can only accept spitballs if it's coming to me at a certain power. A lot of times the range on these might be 15 to 25 decibel. So if a spitball ends up getting to this house and it's 26 decibel, there's no internet. It doesn't matter if this is a 1 gig circuit or a 100 gig circuit. It's not about bandwidth. It's about the light level or the power that it's going to be able to accept. So a lot of engineers are going to put together a light loss plan. So as they start adding components, figuring out where handholds should go or splices should go, we start measuring. Our lasers are going to inject 40 decibels. At the house, we need to end up between 15 and 25. Okay, cool. Let's dive into this. Let's build our network now, okay? So as we start building our network, all right, well, we're going to need a patch panel at our central office, okay? And we're going to plug in this cord, and that's going to go to a switch here. But this cord is essentially being connected to the cable that's ultimately going to this client's house. So as we build out this network, we decide, all right, here's a handhole. Maybe this is a 144 count cable, and we have a handhole right here. Inside of that handhole, we say, all right, well, we want to get internet to the north side of town, and we want to get internet to the south side of the town, along with get to our customer's house over here. So we're going to put a splice case in here. And we're going to put a splitter in here as well, so that we can now have maybe keep 144 count cables coming out in each direction. Okay, so there's a splice and a splitter in here. It's beautiful writing. All right, so we're designing the network. We're figuring out the best way to get internet to all our people at the lowest cost, and we're putting all these new network elements. So what does that mean to testing, though? What does it mean? All right, so starting out right here with our OTDR. As we plug in our OTDR, the very first event that happens is reflection. And reflection is probably my favorite one. If I had a loss type, yes, that's what I think about, is what is my favorite type of loss event. So reflection. So what happens with reflection is the power, it bounces up. The power bounces up. So as we blow or shoot that spitball into the fiber cable, the power really isn't going up. What is happening is, as this spitball is injected into that fiber cable and traveling this 9-micron core, it's in this dark, sealed environment, and it doesn't see light. It might be buried underground. It doesn't see light. But what happens at this patch panel is we have connectors. When we plug those connectors in together, it is this small little air gap, less than a micron, so incredibly small of an air gap. So what that air gap does is the laser is being blinded by light with this small little air gap. As it's a reflectometer, right, that OTDR. So all of a sudden it's getting a blast of light. I like to always use the analogy of you go to a bar during lunch to get a hamburger, and there's not a lot of windows in there, and then you walk out, and whatever, it's 12:30, it's a bright sunny day, you walk out and you're just like, holy smokes, I can't see. Your pupils get blinded for a couple seconds. You're confused, right? And obviously your eyes adapt. That is the same thing that is happening with our lasers or with our OTDR. It sees that gap and it gets confused. And we'll talk about launch cables next, or not next, later. So this is reflection. It's essentially confusion. And we'll write that down over here. So it's confusion. And one thing related to this is connectors. Some of you might wonder what's the difference between a UPC connector or an APC connector. This is a UPC connector right here. And now let's replace that connector and make it an APC connector. An APC connector is just going to create less confusion within that network. So it creates less reflection. All right, so with our connectors, we have a reflective event, but we also have loss associated with them. And that difference is right here. So we're starting at 40 decibel power. And just by adding that connector, in our analogy, we might be losing 1 decibel power. But the measurement from here to here, this is also loss. That is the loss associated with that connector. And talking about connectors, the loss associated with the APC connector or UPC connector, they're going to be about the same. It's just this reflective event that is going to change. So a UPC connector has a lot of reflection associated with it. All right, cool. So we just went through our patch panel. Now we're going a couple miles down the road. We might be at mile 1.5 right here. And we come to a handhole where that splice case is. Now with that splice case, we're going to have a fusion splice inside of there. And as our spitball goes through there, there's going to be slight imperfections in that splice. If you've ever seen on a splice screen, you'll see sometimes just a teeny tiny line, or the machine will give you an estimate and it'll say 0.02 dB loss or 0.00 dB loss. A lot of times there is still a little bit of loss associated with it. So what does it look like on this chart? What happens here at this handhole is we're going to change this line, and here's our splice point. What happens is the power is then reduced. So that reduces, and this line that we used to have that went straight to that house, it still continues on that straight trend, except for now it ends up possibly at 20 dBs at the house here. So that splice reduces our power. And this does not create any confusion. It's a single moment in time and distance. So another type of loss event that we hear about is with splitters, and it looks the exact same. So let's say that this was a splitter. And if you're very briefly a splitter, we have a fiber coming in, and it goes into something about the size of a pack of a Wrigley baseball pack of gum. And inside of it is a diamond that is just reflecting the light in different directions. So now we have a 1x4 splitter. There's now 1, 2, 3, 4 different fibers coming out of this splitter. Okay? So the power of the light being injected into this, we lose a lot of power. So it's a larger loss event here. So this event, so if we are at, right now we're at approximately 30 dB. So if we're at 30 dB, that light's being split up, and on the output side of each one of these, it's a huge loss event. This might now drop down to 25. And the larger the split, so we got 30 coming in, 25 going out. So now with that splitter, Now we lost even more power. Now we might be right at, let's say we dropped a couple extra dBs there. Now we're at 18 decibel, okay? So at this customer's house, we're still within this window. This person's still happy. They still have internet. They can stream their school at home. So we have our splice point splitter, and that was a huge loss by adding that splitter. But it is the same type of event over here. So a splice and a splitter. So one of the last ones we're going to troubleshoot is probably the most fun. Again, make sure that if you're unfamiliar with wavelengths, go and watch that first video on kind of the principles of wavelengths. So we're shooting our customers, they're running their network. Remember, the reason we're getting out our OTDRs is to try to find troubles or issues with our network. So we're running our network and the customer calls and complains. Says, I don't have internet, I can't stream my schoolwork, whatever the scenario is. So they get out the OTDR. They shoot their OTDR, it sees all these events, and these events can be very planned out, highly engineered. This is our light budget we're kind of looking at. But remember, it's going to be engineered so that it works. So right now this was engineered so we'd be at 18 decibel when the light got to that ONT. Perfect, these people have internet. But they're calling, complaining, what's going on? Get out the OTDR. So we shoot the OTDR. And whenever we are testing with an OTDR, we are always shooting at two wavelengths, 1310, 1550. 1310 is a hyper wavelength. It's an El Camino car. It can go through turns real easy, real fast. So as we use our OTDR, we shoot our spitball. It goes through the patch panel, through that connector, goes through the splice point into the splitter. That's fine, 1310, it's flying through there. And it goes all the way to the house, and it says, hey, I'm good, man, I got here. I'm El Camino, I'm cool. And then the OTDR also shoots out 1550. And 1550, let's think of that as a long bed pickup truck. All right, so now that spitball, 1550, goes flying through here. It sees the connector the same way 1310 does, and it goes down our cable, goes through the splice point and splitter. Same effect, doesn't care. But now as 1550 goes through here, 1550 does not like something that is happening right here. It's telling me, hey, we got an issue. I'm at 12 dB of power. 12 dB, why is 1550 not working? Huh. Well, that is probably the reason why this customer is happy that, yeah, we're out of their ONT's range of acceptable light. Well, what the heck? 1310 went flying through here and said it was fine, but 1550 isn't working. It's a bend in the cable. Because 1310 is that hyper light that it can go through tighter micro or macro bends than 1550 could. 1310 is that El Camino, it can make a U-turn really easy. 1550, long bed pickup truck, not quite as much ease turning around. So that's why we really want to test with two wavelengths, so we can then kind of spot check, because 1550, it is unhappy right here. 1310, it did not know any difference. But because we can reference them, this event that looks like it could be a splice, if we had only tested 1550, we might think this is a splice. But because we tested at 1310, 1310 said it was fine, we're able to deduct that it is indeed a bend in the cable. And that is a pretty decent summary on testing principles. Let me know if you got any questions on this. This is very simplified, but it should give you a good base to help spec your clients' OTDRs and understand wavelengths and what they're asking to do.